So I think we can start. So as the title suggests, we're going to do something new today. But before I go there, let us first wrap up what we were discussing in the last lecture. And from there, we should that will naturally motivate us about the need for this higher order or second order method in this case, right? So till now we have discussed about FOSM, first order second moment method, and in FOSM we have discussed about MV-FOSM, which is the mean value first order second moment method, and AFOSM, which is the advanced first order second moment method. In AFOSM, which is the advanced first order second moment method, I told you that that is nothing but the form, first order reliability analysis method, right? And first order reliability analysis method is based on the definition of beta that was proposed by Hassoford and Lind. We do not use the Cornell's definition of reliability, we use the Hassoford-Lind definition, right? And that is what we discussed. And if you remember, in the last lecture we started discussing about the algorithm, the form algorithm, and that is where we kind of wrapped up. So let us start by recapping that algorithm, and from there we will see where we go, right? So in the last lecture we discussed form. In the last lecture, right, we started discussing form and we kind of completed it also, which is the first order reliability method. Let us look into the algorithm, the exact algorithm with which we ended. And this is the generic algorithm. So that means it can handle non-normal random variables. So it should be able to handle it. What was the first step? Initialize. And you will initialize what? You will not initialize z in this case. You have to initialize x because you have to transform it each and every time. So you will initialize x. So let's call it xk, which will be equal to x naught. And in absence of any other information, what will be this x naught equal to? Mean, not 0. Z was 0. This will be equal to mean. So this is generally mean, right? And then step 1. What was step 1? Correct. We will find zk, but for finding out zk, we have to find out the mu equivalent and the sigma equivalent. So this is step 1 is find mu equivalent, and we are at the kth step, let us assume, and sigma equivalent, I am at the kth step. Step 2, I will use this to find out my z. Step 2, find z. Okay. And how will you find it out, zk? Zki is equal to xki minus mu equivalent ki divided by sigma equivalent ki, and you will do it for all the I. So I will go from 1 to k. I am assuming capital K is my number of random variables. Small k is my iteration, the loop counter, right? That is what I am assuming here. Okay, I have my zk. Step 3. Now nothing changes. I will compute gradient, grad of z, g of zk. I'll do that, right? Step 4. I'll compute my alpha, the unit normal in the direction of the gradient. So step 4 is find alpha, which is alpha k is equal to z g of z k divided by the norm, and that basically is your unit normal vector, right? So this is my alpha k. Next step, update beta, so you will get beta k plus 1. Step 5, update beta, which means basically beta k plus 1, and it is equal to, we know that, grad of z g z k transpose z k minus g of z k divided by the norm g of z k, and that is my updated beta. Next step, I will update my z. Step 6, update z. So z k plus 1 is equal to alpha k beta k plus 1, right? Next, we will transpose or transform z to the actual space. So transform z to x. Why is it needed? This was not needed earlier, because the normalization that we are doing is the local normalization. We have to do it every time. Okay. So step 7, update x, and so that is equal to x, k plus 1 is equal to mu equivalent k I plus sigma equivalent k I z k plus 1 I, right? And this you will do for all I. That means you will have to do it k times, capital K times. And then you will repeat step 1 to step 7 until convergence. So this is the form algorithm that we discussed over the last 2 lectures. This is the gist of it, right? So repeat steps 1 to 7 until convergence. And by now you know what it will return, so I am not writing that. You know that it will return the design point at convergence, it will return beta at convergence, and it will return probability of failure at convergence, and you are aware of that. So I will not go and discuss that. I will not go and discuss that. Okay. So that is, you are aware of that, so I am not discussing that, right? Okay. So this was form. This was form for non-normal variable, but there is a even more advanced version of form, a more generalized version of form. Can you imagine what that will be? What is the thing that we have not considered till now? No, that's an improvement over form. I am talking about form. Is there some case that this form algorithm will not be able to handle? Forget about accuracy. I am only talking about it will not be able to handle. See, although I have assumed the variables to be Gaussian, I assume them to be independent. But it is not necessary that the variables will be independent or uncorrelated. The variables might be dependent. And if that is dependent, this transformation fails. This transformation is assuming x is independent, x are independent, right? So I will not cover that case, but I will give a homework on that. It is for your self study. So in homework 2 you will get a question I was making it yesterday, where you will have correlated random variables. And so study it on your own, do it. Okay. Why this transformation? I am doing each variable at a time. Where is the covariance term there? If it is correlated, then xk1 and xk2 will be dependent. So that information should come somewhere. Covariance. Do you see that covariance? I am talking about a normalization of xki and xkz, xk1 and xk2. But if they are correlated, what happens to z? Will z be independent or they will be dependent? If x, the samples are dependent and you do the same transformation, z's will be dependent. They will no longer be orthogonal. Remember, the whole idea is that z's are standard normal. Standard normal means variance is equal to 1, mean is equal to 0, covariance is equal to 0. That's what standard normal is. So it is violating that thing. So to summarize his question, or to summarize the answer to his question, you have to keep in mind that the form derivation is in the standard normal space. Now, when I say standard normal, in your mind you think about 0 mean unit variance, but that is a univariate case. In multivariate case, standard normal will be 0 mean diagonal covariance with 1 in the diagonals. That's the standard normal in multivariate space. Okay. Okay. So this will fundamentally not work directly. You have to do some additional transformation using Cholesky decomposition, which you study on your own and do it in the home. Okay.
For the small k iteration, it would be under that I or I would be under that k.
K is the outer loop, right? Obviously. I, you might decide not to even iterate. You can, if you can form a matrix, you can do it directly. I is not an optimization loop. I is just that you are computing one at a time. K is the optimization loop, right? Okay. So that is all about form. One aspect I am leaving, and that is for your self-study. I am supposed to have 25% self-study, and there is the guideline for 700 and 800 level courses, by the way. So this is part of that. Okay. So now, even if it could handle correlated variables, and it can, with some transformation, it can handle correlated variables. Can you think of what are the potential source of error or approximation in form? So when form fails or why form fails, if someone asks you, what will you say? Why form might fail? So can you tell me some reasons? We just discussed the whole algorithm. So from the algorithm, you should be able to think and tell what are the approximations that are there. And in the generic sense I am talking about, okay, not in the Gaussian sense. Let us go back, right? What was step 1 and step 2? Transforming x to z, right? And this we are doing locally. Do you think this approximation is exact? No. And that is the reason we are doing locally. If it was exact, we had done it globally. So one source of approximation that is coming is from the Haushofer-Lind way of transformation. So this is known as Haushofer-Lind transformation in many books. Okay. So this transformation that we are doing, the probabilistic transformation from non-normal to normal, is one source of error that we are introducing into a system. So point number 1 is probabilistic transformation. Okay. In this case, in form, we are using the Haushofer-Lind transformation, which is the local transformation, that is the name. And that's an approximation that is introducing. If that is not correct, you are in trouble. You will get erroneous results, right? What is the solution to this? The solution to this is to use better probability transformation. We know from theory that any distribution can be transformed to any distribution exactly, given some assumptions, obviously, that some quantities you can compute, Jacobian and all those things, you can do that. So we should use better transformations, and that can potentially address this. Now I have already talked about, not discussed, just named, two transformations that we will discuss sometime in this course. What are those? Rosenblatt and Natab. So Natab transformation, you will actually need to handle the correlated variables, by the way. Natab and Rosenblatt. So this we will not discuss today, but these are ways to have a better probabilistic transformation from non-normal to standard normal. Okay. Any other source of approximation in the algorithm? So step 2. Step 3. Is there any approximation that you can think of? Step 3 is computing gradient. So can you think of some approximation here? Last lecture I gave an example where this will be approximate. Correct. If you use finite difference to compute it, that will be an approximation. So second source is, and this might not always be there, but assuming I am using finite difference, which we will have to use in most cases. So gradient computation, and this will only be there in some few cases. I mean, if FD is used, otherwise it is not there. If you use computing in exactly, if you can compute it exactly, then that's fine. That is the second source of approximation. Step 4, is there any approximation? No, that's the definition, right, of unit normal vector. Step 5, is there any approximation? Taylor series, first order Taylor series. So step 5 is an approximation. So the third one is, we are using first order approximation or first order Taylor series, and that is a big approximation, right? And after that, everything is based on the Taylor series, so everything else can be improved if we can improve that. So these are the three potential approximations that are there in the form algorithm. And how can we address them? Let us see. Probabilistic transformation, I already told you that you can use a better transformation. Computing gradient, you can compute it analytically for analytical function, but what if you have a finite element, then what will you do? There are methods such as adjoint method, which allows you to find out the gradient quite accurately. You have to just form an adjoint equation and solve the coupled system. With one additional single solve, you can get the single linear solve, actually you can get the adjoints, and from the adjoints you can compute the gradients. I will not discuss that, but if you are interested, there are adjoint methods which you can use. Okay. You can also use something nowadays which is known as differentiable solver or differentiable physics. That's a domain now, where you develop solvers which allows you to do differentiation using automatic differentiation, chain rule. So if you are using such a solver, you can compute the gradients exactly. So that is how you can address that. But finite first order Taylor series, that if you have to address, you have to use higher order Taylor series, and that is where second order reliability method or SORM comes into picture. SORM was proposed as a way to relax to a certain degree, because second order is also an approximation, but a better approximation, to relax to a certain degree this approximation number 3, this first order Taylor series approximation. Okay. Okay. So now let us try to understand what kind of error this first order Taylor's approximation introduces in your system. Okay, graphically. I mean, not that difficult. We're not doing maths, but graphically. Okay. So now we are always in the standard normal space. Keep that in mind. Okay. So this is my Z1, this is my Z2, and in realistic sense, this will be much high dimensional actually. We started with it by capacity minus demand, and from there we arrived. But in a generic sense, it might have 100 random variables. So you might not be able to draw it. And let's say my limit state function in the standard normal space is something like this. Possible? Now what is form doing? Achha, by the way, before that. So this is my g of z equal to 0. This is the equation, right? This is my failure zone. And this, what you are seeing, is my safe zone. Right? And you can imagine that if the car moves towards the failure zone area will reduce. So as a result, the probability of failure will reduce, reliability will increase because the distance is increasing. So from the definition of beta, you can easily follow that, right? But now, in form, what are we doing exactly in this graph? We are finding the minimum distance, point on this curve which is nearest to the origin, and then at that point we are doing a first order approximation. That is what we are doing essentially. Everyone follows, right? Now, when you are doing it and like this and computing it, what can you tell me about this area? What is happening to this area? This area was actually in which domain? Safe domain. Because of form, this is going in the failure domain, which means we are overestimating the failure, probability of failure, or will basically this is the zone we are overestimating, failure. Clear what is happening? Now you can argue that why the limit state function will be of that form. It can be convex or concave, it can be opposite of that also. So let us see what will happen in that case. So suppose my limit state function now, again z1 and z2, and now my limit state function is something like this. Also possible, okay? And let's say, from the diagram it might seem this is the nearest point, but let's say this is my nearest point, okay? It's the mistake of my drawing, but assume that is my nearest point, okay? Nothing changes. So if that is my nearest point, what I will do? I will draw a tangent like this, right? And now in this case, originally this area was what? Failure. Now I will call it, so it will start underestimating. So now, can you tell me, so what are we missing here? From both this diagram, can you imagine what are we missing? We are missing something here. We are taking a straight line, so what are we missing? Curvature. We are not introducing or including the information about the curvature. If you include it, the two curvatures are opposite of these two diagrams, and that should account for the fact one curvature will be negative, and we will tell you no, you are taking beta to be more, reduce it. The other will say no, you are taking beta to be less, increase it. So the curvature information we need to bring into picture. And how do you bring curvature information? By going into second order. So if I do a second order, before I go to the math, what will happen in a second order? Remember, I will repeat, second order is not exact. So when you do second order, you will do about this point and you will probably get a second order approximation, right? So something like this. In this case, you will end up with a second order approximation. right? So the orange line that you see is my second order approximation. It is still an approximation, but you can understand that the error will reduce. So that is basically the motivation for going from first order reliability method to second order reliability method. Okay. So this is my, let me write it down. This is my second order approximation. By the way, what kind of curve will you get in second order approximation? Quadratic, but mathematical term. Quadratic is also mathematical, but geometry, parabolic. You will get y is equal to x square, x equal to y, something like that. You will get a parabolic. We are doing a parabolic approximation in second order because we will stop at second order. So you will get something like y equal to x square, something like that, which will basically be parabolic. So this is also second order. Okay. So with this background, oh, by the way, it's clear, right? The second order thing. So with this background, now the question comes, how will we bring curvature into picture? How will we update our belief or the reliability or the probability of failure? And what is the mathematics behind that? How do we arrive at some formula that has information about the curvature, right? So let us go there. Okay. Okay, one thing I will like to mention additionally, you should always keep in mind that second order reliability method is an improvement over first order reliability method, and that is kind of obvious. But when you keep this in mind, also keep in mind that for solving second order reliability method, you first need to solve the first order reliability method. You need to form the form, and then form is a post processing or some additional steps over form. Why is it so? Because in form, what are you trying to find out? Design point. Form approximation is also about the design point. So if you don't know the design point, z star or x star, whatever you call it, how are you going to even write that approximation, the second order approximation? You first need to solve the form and then use this to do it further. It's not some approximation about mean. It's not. It's approximation about the design point. So that is why you should treat it like a post processing. Okay. Okay. So now let us start discussing second order reliability method. And without a doubt, this derivation or whatever I am going to do will not end today. We will only do up to a certain point. You will not see the final update, and we'll stop there, and we'll continue it from there tomorrow. It's not possible to complete it in one lecture. So leave alone in what, 20 minutes? I'll not be able to do that. Okay. So first let us do the Taylor series expansion about design point in the standard Gaussian space, right? So g of z, and this z is some point on the curve, limit set function. Okay. This is equal to, or I should write approximately equal to, g of z star plus grad g of z star transpose z minus z star plus half z minus z star transpose grad of z square. So that is the second order derivative, g of z star z minus z star transpose, not transpose, sorry, this transpose is not there, right? Simple. This is what we are going to do. Now z star by definition is on the limit state function. So what is g of g star? 0. I am assuming z is also on the limit state function because second order, so at least near the point it will be on the surface before it goes away, because it's not a tangent any longer, right? It's a second order, so it might be for some time it will be on the point. So that is also 0. So what do I get if I put 0 and 0? So first of all I said z star is on the limit state, and this too we know, this is the definition, and this implies g of z star is equal to 0. I am also saying that z is also on limit state. So g of z is also equal to 0. So z is some nearby point of z star, and because we are using a second order approximation, we can assume that. Okay, for first order you cannot, because even delta will be not be on the point, because it's a tangent, right? Right. So what do we get with this? What is the expression now? 0 is approximately equal to 0 plus grad of g z star transpose z minus z star plus half z minus z star transpose. Now there is a gradient term, the second order gradient, that is nothing but the Hessian. So let's call it, I don't want to write grad square, I will call it H. H is the Hessian, right? So Hessian and then G minus G. Okay, where this H is my Hessian matrix. Okay. Any question? Clear, right? So now we are going to do some variable transformation. Okay, we are going to do some variable transformation, and let us see what we are going to do. So how was our limit state function? Let's assume that. Okay, so let's say my limit state function was something like this. Okay, this was my design point, and at this point the form was something like this. The form is going to be something like this, but that is not important. What is alpha here? What is the direction of alpha? Normal, I mean in the direction of beta basically. So beta is where? This one. So this will be, let's say, either in this direction or in the other direction. It depends what convention you are using, but it is perpendicular or to that at that point, perpendicular to the tangent plane, as you call it in linear algebra, or it is towards the gradient vector, right? So what I do is I transform this coordinate system. So z1 and z2, I transform it, so I rotate it such that one of the axes is along alpha. I transform it so that one of the axes is along alpha. Why am I doing it? Because that will reduce some variable, make my life easy. There is no other reason for doing it. The only reason I am doing it is that if the parabola, that is parabola, the second order approximation. If I go in that direction, I can write the expression very easily. It will be in that transformed y equal to x square or x equal to y square, something like that. I mean alpha you can include, but it will be like that, right? And that is why I am doing it. There is no other reason for doing it. I am doing it for mathematical convenience, because otherwise with the Hessian the curvature information is already with me. Now to make it simpler, the expression easy to calculate, I am doing it. So what we do here is we transform the coordinate, we transform the coordinate, and how do you transform? By multiplying with a rotational tensor, which is a matrix basically, but a rotational tensor, right? So let's say that is R, right? Where R is my rotational tensor. It will have sine and cos kind of things, right? Okay. So I can do that. I mean, from solid mechanics, you all know that. I mean, this is what we do for principal trace and all those things. I'll come there. But you know that rotational tensor, you have done it. Where this Z star that you are saying, how will it look? What is the first component of this Z star? I just told you. How am I transforming it? Along the alpha. So what is the first component? What is the unit normal? The first. What is Z1 tilde? Alpha. Alpha is the unit vector. I am asking about unit vector. So in this direction, the unit vector is alpha, one of the basis vector, and the other is something orthogonal to that, Q. Okay. Now if I generalize, and I am giving you a statement which is generalization of this, you tell me if you are able to follow or not. I am saying alpha, this vector, is one unit vector. Okay. So its dimension will be whatever the unit vector dimension is, right? But Q, the Q is actually k minus 1 unit vectors. Do you follow when I give this statement? I will repeat the statement. I am giving a statement. Alpha is one single unit vector, and that we know, it is along the gradient. Q is k minus 1 unit vectors. Do you follow? And k is capital K. And what is capital K? You know. So do you follow that? It is simple because here I had written Z1 and Z2. In reality, you will have Z1, Z2, Z3, Z4, Zk. When you transform it, you will get Z tilde 1, Z tilde 2, Z tilde 3 up to Z tilde K. Now this Z tilde 1 will be my alpha. Everything else is written together in Q. So that is why it is k minus 1 unit vectors or k minus 1 basis vectors. Clear? Clear? Okay. With this in mind, so what will be the dimension of Q, by the way? K minus 1 cross K or K cross K minus 1, something like that. If you take like vector, so each vector will be K dimensional and then K minus 1 such unit vectors, right? Like if it is in 3D, then it will be 2 cross 3 or 3 cross 2. Okay. Okay. So if it is clear up to now, let us do one thing. Let us go back to the Taylor series expansion, and in the Taylor series expansion, I see one term which is Z minus Z star, right? So in the transformed coordinate, in the transformed system, which means coordinate system, Z minus Z star, I can call it delta Z, and that's fine, right? And we always do that in Taylor series, nothing new. See if I can write it like this: S alpha plus Q T. See if it is making sense or not. How do you write a vector using the vector notation, using the unit vectors? Suppose it is 3D, then it will be A I cap plus B j cap plus C k cap. You know that, right? If it is a k dimensional vector or n dimensional vector, it will be A1 I1 cap plus A2 I2 cap plus A3 I3 cap plus A4 I4 cap. If I go beyond 3D, it will be like that. That same thing I am doing here. So S is the magnitude in the direction of the normal multiplied by the unit normal in that direction. And then Q times T is there. So Q is having all those direction vectors for the k minus 1 terms, and T is having those k minus 1 magnitudes. Yes, what is it? Depends how you are writing Q. If Q is, what is the dimension of Q? You know, k cross k minus 1. Each one is k, and then you have k minus 1 such. Right? T, what is the dimension? How many directions you are going? K minus 1. So you will have k minus 1. So k cross k minus 1 multiplied by k minus 1. So that's why we written it like that. If I write Q as k minus 1 cross k, then T will come in the. So it depends how you are writing it. So matrix, right? So the dimension of alpha, so let me write it here. S is basically a scalar because it's a magnitude, a single magnitude in the alpha direction. T, I'll write later, okay, alpha, it's a unit vector. So unit vector, the dimension will be k cross 1. So I'll write RK, capital K, right? Q is k minus 1 unit vectors, right? So this will be R k cross k minus 1. That is how I am writing it. And then T is magnitude in k minus 1 directions, written as a column vector. So T is R k minus 1. And now you can understand why I have written QT and not TQ. You can write TQ, but then transpose it and manage that. Okay. So that is why I have done that. Okay. Or you can write Q transpose T also. I mean, all those things you can play with. I mean, that's not a problem. Okay. Any doubt on this? Okay. What? Q. Okay, very simple. Suppose I have a vector in 3D, A, and this is my x, y, z. How do you write it? A is equal to A1 I cap plus A2 j cap plus A3 k cap. You do that? So now can I not write it as? AC switched off, right? Yeah. So can I not write it as A1 I cap, that I will keep as it is, and the other two I am going to combine. So let's say I am in XYZ. So what is I cap? 1 0 0. What is j cap? 0 1 0. K is 0 0 1. This second and third I will combine. So what will I get? I will get j and k. What is the dimension? 3 cross 2, because j is 0 1 0. So 3 row and 2 columns multiplied by A2 A3. That is what I have done in there. Nothing difficult, but the only problem is that I am not in reliability, you are working in k dimensions. It's not 3 dimension or 2 dimension that you can visualize. So we need to do it some compressed representation. Okay. The variables are not independent. This is only in the standard normal space. So that's the assumption. It is valid for any coordinate system, as it's valid for any coordinate system.
The variables are not independent. We're transforming it in alpha and q as bases in this new system.
Alpha and q are unit vectors, basis vectors, right?
And q contains all the like all of the vectors, all of the variables. So if
Q does not contain variables, it contains the basis.
Those are not, if Q and alpha seem it.
I mean, the whole idea of basis is that they are unit vectors and orthogonal, right? And that is the whole definition. You are violating the definition of basis function then, what you are saying. But I understand your question. The broader question is that, is this representation valid? It is, if it is valid for IJK Euclidean system, it is valid for cylindrical system, it is valid for any coordinate system. Anything that you can write in terms of basis, it is valid.
These two independent.
They are orthogonal. They are orthogonal, and that will come very soon. Then, because the moment I have written this in this manner, Q and alpha are orthogonal to each other. Okay. If they are not orthogonal, some of the derivations will not hold, which will follow. Okay. So this is clear. Any question? So now, one more thing. What is, how can I write this in the alpha and Q code basis? What will this be in alpha and Q basis? This you should be able to tell. Grad of G at Z star. In alpha and Q, this coordinate system. In the transform coordinate system, how will you like it? Write it. What is the direction of alpha? In the direction of gradient. So this is the gradient in the direction of alpha. So then what will be the magnitude? How do you write some point which is on the x-axis? Same thing. Into alpha, right? Simple. I mean, it's simple. If a point is on the x-axis, it's a I cap and b and c become 0. So in the same sense, this will be magnitude. And this we already know. We have used it last to last lecture, I think. This we have used last to last lecture, right? So now let us take these two expressions and substitute it into a Taylor series. Okay, and see what we will get. So I will get 0 approximately equal to I have grad G transpose, right? That will be equal to Z star, and this is a magnitude, a scalar value, so that I don't care about, alpha transpose, right, multiplied by Z minus Z star, which is delta Z, which is equal to what you are seeing at the top, S alpha plus Q T. This is the first term, right? Clear? What will be the second term? Half S alpha plus Qt transpose H S alpha plus Qt, right? Because it was Z minus Z transpose, that is S alpha plus Qt multiplied by H remains H, and then Z minus Zt, that becomes S alpha plus Qt. Any doubt? Hessian I am not transforming now. You can, but not doing that. Hessian I am keeping as it is. Okay, clear? What happens to the first term if I do the multiplication? Use the orthogonality property we were mentioning. Not only orthogonal, orthonormal. Alpha transpose alpha is 1. Alpha transpose 0. So what will you get? So this is equal to grad exactly G Z star S, right? And the second term, I will need 5 minutes for that. I don't have the time, so I will not do that for second term today. We will start with the second term, because in the second term there will be many approximations that will come from the fact that it is parabolic. So I will start with the second term tomorrow. So for now, I'll end it by writing the second term as it is. Transpose H S alpha plus Qt. The second term itself will take 5 minutes. Okay. So we have not done anything about SORM now. We have just started it, but we at least have discussed the motivation of SORM, which is the most important part. Okay. Derivations are important, but the intuition is more important, and the algorithm is the most important in my opinion. If you understand the algorithm, you can do it, and you will also understand the fundamentals in that case. But if you don't understand the fundamentals, you will not be able to write the algorithm, not able to do it. So that's how I see it, at least. I mean, some may disagree, but that's how I look into it. Okay, so I'll stop here. Next lecture, which is tomorrow, we'll start with this second term, and from there we'll try to define or find out probability of failure in this case. Okay. Okay. Thank you.